So welcome everybody to our theory of the gamma seminar, sorry. Today we have the pleasure to guest Piergiulio Tempesta from the University Complutense de Madrid and the Instituto de Ciencias Matemáticas in CEMAT. So thank you, Piergiulio, for accepting our invitation. It's our real pleasure to have you here. And today Piergiulio is going to talk about Haantjes, geometry, and Hamiltonian integrable systems. So once again, thank you for accepting our invitation. The floor is yours. We listen.
So, first of all, thank you very much to the organizers. I'm really grateful to you for this opportunity. And today I will talk indeed about entire geometry and multiple applications to the theory of Hamiltonian integrable systems. Okay, so the idea is actually to generalize the theory of Nijenhuis operators, which, as we know, after essentially the work of Franco Magri in the 80s, not only are relevant in differential geometry, this was already known before, of course, but also they are relevant in the study of integrable systems, both finite and infinite dimensional ones. Also, Falqui, Pedroni, and other colleagues indeed intensively used Nijenhuis geometry in order to study integrable systems. So, in other words, the purpose is somehow to develop the geometry of entire tensors more or less in the same way as Nijenhuis geometry has been developed in the last decades. So we are especially interested in tensor analysis, generally speaking, and of course Hamiltonian classical integral systems, and many other possible applications, including hydrodynamic type systems. So,
sorry, Piergiulio, I said to you, we used to interrupt a little bit. Can you comment a little bit more about hydrodynamic type systems? Because I've been working with. You will talk, yeah.
Of course.
Okay. So, yeah. Okay,
this is
so great.
just the really introductory slide, so don't worry.
Yeah. Fine, thank you.
Okay. So, in particular, so in a nutshell, results will be the following. First of all, from an algebraic point of view, I will present some new algebraic and geometric structures, precisely the omega H manifolds, also called the symplectic-Haantjes manifolds. Okay, omega indeed is the symplectic form, and H we refer to an Haantjes algebra on top of this symplectic structure. Then we will talk about a generalization of the both Nijenhuis and Haantjes tensors, meaning the idea of a tower, infinite tower of generalized Nijenhuis torsions on level M, where M is an integer number. Then I will talk about Haantjes algebras and their generalizations. Essentially, this framework gives us an alternative perspective about classical notions like integrability, superintegrability, separation of variables. So everything can be discussed and reinterpreted in this Haantjes geometry framework. And also, I would like to propose, this is perhaps the most relevant theoretical result, a generalization of the classical Haantjes theorem, which guarantees as a sufficient condition the integrability of the eigen-distributions of operator fields. Okay, so then this is to line. Essentially, we have three parts, an introductory part, which is also historical. The second part will be the theory of this symplectic-Haantjes, or in short, omega H manifolds. And then the third part will be devoted to generalizing Haantjes geometries to, let's say, more exotic frameworks. Okay, so just to fix the notation and to propose some basic definitions, of course, we denote by M a differentiable manifold of dimension n. With this symbol, of course, we denote the algebra of vector fields on M, and then essentially we'll deal with one tensor fields. In short, we say operators to denote to say a one tensor field. Okay, and the spec A, of course, will be the spectrum of an operator, and in particular, we denote by this symbol the eigen in the let's say generic eigen-distribution of a given operator with Ritz index rho I. Okay. Again, I have to also point out that we will need a sort of regularity condition, meaning that the rank of these distributions will be independent of x. Of course, this condition although generally speaking is, let's say, standard, could be, of course, relaxed, and this would brings us to more general notions of integrability. Okay.
Sorry, Piergiulio, and just a curiosity, why the name risk index? I mean, this is like in the algebra, yeah?
Exactly, because it's exactly the same meaning, essentially. Rho I here a priori could depend on X, okay? But here
yeah, sure.
does not.
The shocking for me was the name, because, you know, normally it's just called the multiplicity. It's,
well, yes, maybe it's more, I think, maybe it's a bit more clear if we refer to the Ritz index in the classical.
Sure. Okay, thank you. It was just a curiosity.
Yeah, of course. Thank you. So from a historical, well, let's say not only historical, but also conceptual point of view, maybe the starting point for us could be to think again to some classical problems in differential geometry. Precisely, the first problem, which actually in full generality is of course still open, is the following. So if I have an operator, meaning a one tensor field, of course, defined on a manifold M, we wish to have or to construct local charts in which A takes a simple form, where simpler could be diagonal, of course, it would be the best possibility, or block diagonal, or triangular. Let's say, indeed, a more tractable form for the application. So this can be said or can be defined the problem of the normal forms of an operator, right? So given an operator with certain properties, of course, not a completely generic one, for instance, an Nijenhuis or Haantjes operator or eigenrod operator, which are the normal forms of this operator. Then another question, which is actually directly related to the previous one, is there exists an interval eigenframe, meaning, namely a frame of eigenvector fields of A, which actually can be put in a one-to-one correspondence with the, let's say, natural frame, no? In other words, a frame that can be rectified. Again, this is a fundamental point. There exists a tensorial criterion which allows us to determine whether an operator possesses or not integrable eigendistributions. But this without entering the spectral properties of the operator, meaning that is it possible to know a priori somehow with a criterion if our operator is good or not, meaning it possesses integrable eigendistributions. And also, actually, we are interested also in the integrability problem of the direct sums of these eigendistributions. So both questions are absolutely crucial. Okay, so let's say the first results in these directions were provided by Tonolo, 1949, and Schouten, 51, which actually studied these tensor conditions, but on Riemannian manifolds. Okay, so they were interested in detecting the integrability of operators defined on Riemannian geometry. And the great idea of Nijenhuis, again in 51, was to actually to put the problem in a more abstract setting without the necessity, without the need of a Riemannian structure. So Nijenhuis said, can we answer these questions actually independently on the existence, no, of a Riemannian structure? So then this would be even more general. Actually, he was able to provide a first answer, assuming that the operators considered possess distinct eigenvalues. So in the standard parlance, they are called the simple operators. A simple operator is an operator possessing distinct eigenvalues. Then actually provided a sufficient tensorial criterion for integrability for simple operators. And then the next step was due by Haantjes, who in 55 actually characterized integrability for semi-simple operators, where characterized means that he gave a necessary and sufficient condition for integrability of an operator in the case of semi-simple operators. A semi-simple operator is essentially an operator that possesses a basis of eigenvectors, okay? And also provided a sufficient, just sufficient, not necessary, condition when an operator is generic, meaning non-semi-simple, okay? Then this is essentially the picture till recently. Okay, so more precisely, what is a Nijenhuis tensor? So the Nijenhuis torsion of an operator field is essentially this vector value to form defined by this relation. Okay, so we have four addends, four summands, and of course this symbol denotes the standard Lie brackets, okay, or two vector fields. So what is a Nijenhuis operator? Essentially is a one tensor field whose Nijenhuis torsion identically vanishes. Okay, so for any choice of x and y. So when tau a of x and y is equal to 0, a will be said to be a Nijenhuis operator. Okay, so the theorem by Nijenhuis of 51, which more or less I sketched before, is more precisely the following. So first of all, we suppose that a has distinct real eigenvalues at each point. And then we assume, of course, that its Nijenhuis torsion vanishes. Then each eigen-distribution of A, as well as each direct sum of eigen-distributions, is Frobenius integral. So it's integral in the most standard sense.
Piergiulio, there's a
Yes.
curiosity, because some of my research is devoted to, for example, Darboux coordinates and things of the sort. So now I'm noticing that I could use Nijenhuis torsion and Nijenhuis operators to describe them, because one of the properties they appear in these Darboux structures is that, well, you have said that it's a decomposition into distributions that are integrable in such a manner that when you work out the direct sum of these distributions, they are also Frobenius integrable. Do you know about any application of Nijenhuis torsion operators in differential geometric structures and things like that? Because I don't know if this is something that, yes, I noticed, or do you know that this has appeared?
Absolutely, and also your remark about Darboux is very appropriate, because as we will see in a moment, all this can be combined with Darboux coordinates. So you have Darboux Nijenhuis coordinates, Darboux Haantjes coordinates. So
okay, I see. Yeah.
Yes, at least a partial answer to your question.
It is. Oh, wonderful, because this is very interesting to us. Thank you.
Welcome. So then, starting from this result, indeed, this is already something about what you are asking. So starting from this seminal paper of 51, the Nijenhuis geometry became more and more, let's say, studied, been largely investigated. Of course, first of all, in differential geometry, and later on in the theory, 50 years later in the theory of, well, 30 years later in the theory of integrable systems. First of all, there is a crucial theorem, the Nylander-Niremer theorem, which tells us that an almost complex structure, J, is integrable if and only if its Nijenhuis torsion is 0. So then J should be a Nijenhuis operator. This is absolutely important in complex geometry. Let's say it's a cornerstone of complex geometry. Actually, after the work of Franco Magri, it was discovered that Nijenhuis operator also played the role of recursion operators in the theory of infinite-dimensional integral systems, and not to mention the relevance in the theory of separation of variables for Hamiltonian finite-dimensional integral systems. Indeed, in this I would say publication by Magri Morosi in 1984, because actually is technically speaking is a quaderno of the University of Milan, was never really published. So it's a very nice actually paper. So they introduced the notion of omega n manifolds, which is a symplectic manifold with a Nijenhuis geometry inside. And later on, also Franco and Professor Yvette Konchman-Sparsbach introduced the theory of PN manifolds, meaning Poisson-Nijenhuis manifolds. And more recently, actually, I would like to mention that Nijenhuis geometry has been, let's say, experienced a resurgence of interest because of the work of Bosino, Koniaev, Mateev, and some other collaborators, who indeed published a series of papers on Nijenhuis geometry and many applications, in particular. Also, they studied normal forms for Nijenhuis operators. Again, the theory of dynamic type systems more recently. So I would say that there is increasing interest in this geometry, also from the point of view of applications. It was always important in standard differential geometry, but more recently also in the applications. Okay, just 2 words. Actually, I'm thinking I'm going a bit slowly. So what is an omega n manifold? Is actually a bi-Hamiltonian manifold where one of the 2 Poisson brackets, so let's say the first one, is non-degenerate. And in particular, M is not only is endowed with a symplectic form, of course, but what happens is that if P1 and P2 are the Poisson tensors associated with the 2 structures, then N, so P2 times P1 to the -1, so of course we are assuming that P1 is invertible, is an Nijenhuis tensor, which is also called the recursion operator. So it's a mixture between indeed the symplectic and Nijenhuis geometry. A P-n manifold is another generalization. We have a Poisson tensor and an Nijenhuis tensor N, which are compatible in the sense that N times P1 is still a Poisson tensor, which forms a Poisson pencil with P1 and again a bi-Hamiltonian geometry. Okay, actually, maybe go a bit faster. As Broussais noticed in 1993, most of the classical integral Hamiltonian systems do not admit even a semi-global bi-Hamiltonian formulation. Actually, the existence of a Nijenhuis recursion operator restricts somehow the form of the Hamiltonian system considered. Then there were several, I would say, attempts to essentially all of them are successful to extend the original bi-Hamiltonian theory in order to accommodate.
Piergiulio, sorry, yes. What does it mean exactly semi-global? What do you have in mind?
Well, semi-global in the sense that it's defined at least in an open neighborhood sufficiently.
Okay, understand. Yeah, because these things appear in Lie system, Lie Hamilton system most of the time. They have the Hamiltonian structure. It will be an Nijenhuis. It could be interesting to see what happens. Thank you.
Indeed. So you can exclude that zero measure set essentially of points from your manifold. Okay, in the sense semi-global. Okay, then there are several generalizations which has been proposed in the literature. Actually, maybe we don't have enough time to discuss all of them. Let me just say that there is, for instance, a quasi-bi-Hamiltonian formulation, which actually is quite effective. Also, the idea of Ibort, Maga, and Marmo of a degenerate bi-Hamiltonian structure in a suitably extended phase space, or alternative Poisson structure, meaning that one can start not from the natural Poisson structure in the book coordinates, but one can play with other alternative formulations, and then this, of course, could give more freedom. The theory of the formation of Poisson structures, and so on. Okay, and now let's go to anti-geometry. Indeed, anti-geometry offers an alternative answer to more or less the same questions. Which is quite, I would say, quite general. So this is simply one more geometry, I would say, that answers the same question, but as I also think several advantages. Indeed, first of all, one can discuss integrability, separability for Hamiltonian systems in a sort of coherent, sufficiently general perspective. Also, the standard normal form of operators can be done in this geometry in a sort of natural way, and in particular, Haantjes provided us with another sufficient criterion for integrability for the eigen-distributions of an operator. So, going more precisely into the definitions, if you have indeed a smooth one-one tensor field A, what is the anti-torsion of A? Is once again the sum of 4 contributions is actually technically a vector value to form, defined this way. So what before was a Lie bracket now is tau A, is the Nijenhuis torsion, right? So we use the Nijenhuis torsion, and in each contribution, the Nijenhuis torsion appears instead of Lie brackets. So, of course, if HA is equal to 0, we have what is called an Haantjes operator, meaning a one-one tensor field whose Haantjes torsion vanishes. So, if this quantity is equal to 0, identically, meaning for all possible choices of x and y, we will say that A is an Haantjes operator. Obviously, if A is a Nijenhuis operator, each of these contributions vanishes separately, right? So every Nijenhuis operator is an Haantjes operator, but the vice versa obviously is not true. So Haantjes operators are much more general than Nijenhuis ones. Okay, so then we will see some example, and everything will be, I think, immediately clear. So we have an important theorem, this crucial theorem by Haantjes in 1955, which tells us that if we have a smooth operator field with regular distributions, meaning that the Ritz index does not change, things like that, is constant. So in the case that A is semi-simple, then the result is that one can construct an integrable eigenframe, meaning a frame of eigenvectors of A, integrable, if and only if the Haantjes torsion vanishes. And also what is fundamental is that starting from this integral eigenframe, one can prove that the eigendistribution of A as well as the direct sums are all integrable, meaning that this is a fundamental criterion of integrability. So that the eigendistributions of an operator are integrable as well as the direct sum, if and only if our operator is an Haantjes operator. What happens in the more general case when A is non-semi-simple, right? So we don't have a basis of eigenvectors. Then in this case, the vanishing of the Haantjes torsion is just sufficient, not necessary, to guarantee the existence, once again, of a generalized integrable eigenframe, and also is sufficient to ensure the integrability, once again, of eigendistributions and direct sums of them. So in other words, if the operator is semi-simple, the criterion of Haantjes is definitive. No? The ultimate criterion is a necessary sufficient condition. Whereas if A is non-semi-simple, the vanishing of the Haantjes torsion is just sufficient to guarantee the integrability of the eigendistributions. Okay, let's have a first example. So let's say two examples. The first class of examples are given by every operator on a two-dimensional manifold. So this is a sort of trivial case. Every operator on a two-dimensional manifold is always Haantjes, but in general it's not a Nijenhuis. So already in lower dimensions, we will see the difference between the two kinds of operators. But if we go in n dimensions, and we want to have the simplest example where one can appreciate the difference between Nijenhuis and Haantjes operators, this could be indeed, I think, the answer. K1 is a diagonal operator where each entry depends only on one of these coordinates, right? Lambda 1 depends on x1, lambda 2 on x2, and so on. K2 is again a diagonal operator, but now the eigenvalues depend on all coordinates. Then the point is that K1 is a Nijenhuis operator, but not Haantjes, whereas K2, yes, is an Haantjes operator. So then, of course, Haantjes operators are much more general. So already at the level of diagonal operators, we can appreciate the generality of Haantjes geometry and the difference between these two classes of operators. Okay, very rapidly, actually, let me tell you that Nijenhuis and Haantjes operators are everywhere, also in classical mechanics. The Euler tensor of a massive body indeed is Nijenhuis, was proved by Benenti, whereas we proved that actually the inertia tensor is an Haantjes operator. So in mechanics, in standard mechanics, also this operator actually appear, although maybe is not so well known. The second result is actually quite recent. Okay,
Piergiulio,
so
yes, a
yes.
question. The inertial tensor, when depends on the position, is something that we were working with Bartos, indeed. And it's quite interesting that is a Haantjes operator. We did it not for rigid solid, because everything could be a constant, but we did it for what we call quasi-rigid solids, or in the literature there are several names, that they can change a little bit, but not much, let's say this way. This is what we did, and things of this appear. So do you know any applications for using this to describe, for example, solid rigids or deformation of solid rigids or something like that? Do you know anything like that?
Well, you can think about the existence of privileged coordinates where you can simplify the form of the initial tensor, right? Because as we will see later on, actually these operators admit coordinates where they can be either diagonalized or block diagonalized. So this is
Okay,
the immediate implication. So you can simplify the form of the initial tensor since it is an anti operator.
This is very interesting because we had to do this to study certain systems indeed. We did it with some approximations, but if this is what you are saying is pretty nice because you simplify the form of it and then you can study it more simply. So it's quite nice. Thank you.
Welcome. And of course, then let's go to hydrodynamic type systems. So indeed, anti-geometry can also offer a natural framework for describing the systems. So let us consider indeed a system of PDEs in 1 plus 1 dimension of this form, where U actually is a vector of fields U1, U2, Un. Each of them depends on X and T. Okay, so K is a suitable operator field. So K depends on U. And then the point is that in the so-called strictly hyperbolic case, so K is real and pointwise eigenvalues, the system, like distinct ones, the system is generalizable if and only if K is indeed an Haantjes tensor. This is a beautiful result by Bogolian-Levski, and also it has been studied in the standard two hydrodynamic chains by Ferapontovi and Marshall, also in collaboration with Pavlov more recently. In other words, well, this is actually quite natural, right? Because if K is an Haantjes operator and also has a real and pointwise distinct eigenvalue, of course, it's semi-simple and then it can be diagonalized, as we will see. So it's not somehow surprising a posteriori, but actually what is new was the application to this kind of systems. Okay, indeed, the system then acquires this form, sort of separated one, where these coordinates are the so-called Riemann invariants. Okay.
Piergiulio, sorry again, but I studied this with Grunland, this system, that this Riemann is invariant. We were interested in the case where K depends on more than U, depends on in T or X and the independent variables. Do you know any result about this case or somehow to deal with it?
I wouldn't say no. I would say no at the moment. So K depends explicitly, you mean, on T and X?
Yeah. This is the classical case in what we studied. We added the dependence of T and X, and we managed to do something like Riemann invariants, but they were pretty much difficult. Okay, it was nice to know if you know something about it. Thank you.
Okay, maybe one can think about it, but no, at the moment I couldn't say that there is some reference on this point. Yes, when I read Riemann invariants, I immediately was thinking about Grunland, and but your work on Grunland, I know about it. So
yeah.
Okay, so then as we know, if there is also this semi-Hamiltonian property which has been defined and studied extensively by Tsaryov, one can also associate to the system infinitely many commuting flows, and the system can be solved by the generalized holograph method. So this is, of course, very well known. Okay, now just an input, let's say that I will come back to this later on. So there is life beyond anti-geometry. The answer is yes. So if we think about this operator, this operator number 2, actually this is an integral operator, so it's very simple. So this can be proved directly. The integrability of the eigen-distributions is sort of trivial. But surprisingly enough, is neither Nijenhuis nor Haantjes. So meaning that the Nijenhuis torsion is different from 0, and the Haantjes torsion is also different from 0. There is no contradiction because, as you said, the Haantjes theorem is just a sufficient condition for ensuring the integrability of the eigen-distribution. But this condition may fail to detect the integrability, even in elementary cases like this, because if the operator is Haantjes, then we know that the eigen-distributions are integral. But if it is not Haantjes, we cannot say anything, right? It may or may not be integral. So then there is a big problem. Is it possible to extend the Haantjes theorem, right? And then we come back later to this interesting question. Okay, so once we somehow accept that Nijenhuis and Haantjes tensor are important in many geometric contexts, so there are natural questions that arise. Can we apply the entire geometry to the study of classical Hamiltonian integral systems? Is it possible to generalize Nijenhuis and Haantjes tensors in such a way that we can treat the theory of non-Haantjes operators like the previous one, okay? Or maybe extend to a dynamic system or whatever. Okay, so then let's try to answer these questions. First of all, it is useful to introduce the notion of Haantjes algebra that we define in this somehow recent paper. So what is an Haantjes algebra? First of all, let us consider this lemma by Bogolian-Levski. If I have an Haantjes operator, so its torsion is equal to 0, then also a polynomial in this operator, okay, where the polynomial has coefficients which are functions, actually, smooth functions. Also, any polynomial in this operator with arbitrary variable coefficients is also an Haantjes operator. So this is a fundamental property which does not hold for Nijenhuis operators. So if A is an Nijenhuis operator, the powers are still Nijenhuis, but if you multiply Nijenhuis operator for a function by a function, then you get an Haantjes operator. So immediately you leave the Nijenhuis geometry, you go and write to the Haantjes geometry. Okay, starting from this condition, then one can consider the notion of Haantjes algebra. An Haantjes algebra rank M essentially is given by a differentiable manifold of dimension n, and then we have a set of Haantjes operator which generate a module, a free module rank M, meaning that essentially you can consider all these linear combinations, okay, where A1 and A2 are Haantjes operators, and we assume that again the linear combination with arbitrary coefficient is another Haantjes operator. So this is a definition. So when this occurs, and when also, sorry, the product of two operators, two Haantjes operators is still an Haantjes operator, then we will say that we have an Haantjes algebra. So it is an algebra closed, if you wish, an Haantjes algebra closed with respect to the linear combinations and the product of operators. In particular, if you have the commutativity, we'll talk about abelian Haantjes algebras. Well, a very simple example is given, the most basic one is given by operators which are diagonal, right? So if you have a set of diagonal operators, they have vanishing and torsion automatically. So every diagonal operator is an Haantjes operator, and then satisfy all the properties to talk about Haantjes algebra, even commutativity. But as a particular interesting case, a particularly relevant and special case is given by algebras which are defined by a single Haantjes operator with its powers. Okay, in this case, we'll talk about a cyclic Haantjes algebra. And then in this case, the rank of the algebra is equal to the degree of the minimal polynomial of this operator. So then we can indeed think about the polynomial operators, right, generated by this operator L. And these kind of structures indeed are cyclic Haantjes algebras. Okay. The theorem of diagonalization for these algebras has been proved in this paper. So we can say that if we have a semi-simple Haantjes algebra, so an algebra or an Haantjes algebra of semi-simple operators, of course, then we can find the local coordinates where all operators simultaneously can be diagonalized. So these coordinates indeed are, let's say, shared by all these operators. So then we have the possibility of a simultaneous diagonalization. There is also the converse part of this theorem, meaning that if all operators in a set of local coordinates have a diagonal form, then they form an abelian Haantjes algebra. But more generally, if an abelian Haantjes algebra is non-semi-simple, actually at least one of these operators is non-semi-simple, then we can find the local coordinates where all of them acquire a block diagonal form. Okay, so although in standard linear algebra this would be somehow obvious, in differential geometry this is not at all obvious, meaning that the commutativity of a set of operators is sufficient if they are all diagonalizable to guarantee simultaneous diagonalization Actually, if we are on a manifold, we need an extra ingredient which is crucial, the Haantjes property, meaning that if these operators, even if they are semi-simple, are either do not commute or we have operators which are not Haantjes operators, then there is no guarantee that they can be diagonalized simultaneously. So that's is an interesting situation. Okay, then let's go to the symplectic-Haantjes manifold. So the step further is the following. Now that we know what is an Haantjes algebra, meaning an algebra essentially of Haantjes operators, okay? We can put this algebra on top of a symplectic manifold and defining what is called a symplectic-Haantjes manifold. So we introduced actually this notion in 2014, but then we thought again and we wrote and rewrote somehow our papers, and finally we arrived to this definition. Okay, so which now indeed looks quite simple. So we have a symplectic manifold with a symplectic form omega, an Haantjes algebra, and actually we also ask a condition of algebraic compatibility between these two structures, which is expressed by this relation. Okay, so if this is true, then this can be rewritten, of course, also in this way. Then we will say that the manifold is a symplectic Haantjes manifold. So we have two structures a priori independent, the symplectic and the structure and the Haantjes algebra, but we put them together with this algebraic compatibility. Then what we can do with this? Actually, we have to introduce let's say, a technical definition, the notion of Haantjes chain. So essentially, we will say that a smooth function H will be, of course, an Hamiltonian in the future, no? Generates an Haantjes chain of one form if there exists a basis of operator fields in our Haantjes algebra, such that this is true. Meaning that I start with an Haantjes operator, actually is transposed, and acting on DH, I get another one form DH alpha. Okay, so then we have a chain, an Haantjes chain, and this exact one forms the H alpha are called the elements of the Haantjes chain, and the function H alpha, so defined, are called the potential functions associated to the chain. Let me remind you that a Hamiltonian system is said to be non-degenerate if this condition is satisfied, where Ji are the action variables for the system. Of course, action angle variables always exist in a tubular neighborhood, as we know. So assuming that for a compact manifold, assuming that this condition is satisfied, we can always a priori find action angle variables, and then if this condition is satisfied, the system is said to be non-degenerate. So,
Piergiulio,
yes.
Sorry, have you tried some time-dependent generalization of this?
What, pardon me?
Have you tried to study some time-dependent generalization of this?
Okay,
The function, the Hamiltonian, depends on the time.
Quite recently, yes.
Okay, because from my point of view, it seems quite natural. It could be interesting, but I don't know. I should take, but maybe I could have some examples of it.
Yeah, indeed. It's something which I'm doing right now, actually.
Okay, so it would be nice to know when you will finish. Thank you.
Yes, of course. Thank you very much. Yes. And so why somehow this symplectic Haantjes structure could be relevant? Because actually we can prove a couple of important theorems, important in the sense that somehow generalize the Liouville standard, the Liouville-Arnold integrability in this Haantjes sense. And the second theorem that we will see in a moment will be the generalization of the Jacobi theorem for Hamilton-Jacobi equation. Okay, so more precisely, if you have an omega H manifold and these potential functions of an Haantjes chain, then what happens is that the Hamiltonian systems which we can form with these functions are integrable by quadrature, so in the standard Liouville sense. And actually, vice versa, if we have a non-degenerate Hamiltonian system, which is completely integrable in the Wheeler sense, then we can find an associated omega h structure in any neighborhood of an Arnold torus, given by this form. In other words, there is a one-to-one correspondence between integrable systems and omega h or symplectic-Haantjes structures. Okay, so with the given integrable system, if we can indeed somehow construct an omega h structure by this relation, and vice versa, if we have an entire chain which of course generates an omega h manifold, then we have the integrability by quadrature. Okay, now let's go to Darboux-Haantjes coordinates. Okay, so a set of coordinates which at the same time are Darboux, meaning that the symplectic form acquires, of course, this standard. In natural form, and at the same time each Haantjes operator acquires a diagonal form, then we will say that these coordinates are Darboux-Haantjes. In other words, Darboux-Haantjes coordinates at the same time ensure the Darboux form of omega and the diagonalizability of our operators. Then what is interesting is that if we have a semi-simple omega h manifold or symplectic-Haantjes manifold, then yes, there exists this Darboux-Haantjes local coordinates. In other words, we can diagonalize simultaneously our algebra and write omega in the simplest possible way, right? But no, this is not the end of the story, because if we have these Darboux-Haantjes coordinates, then what is nice is that there are at the same time separation variables for the Hamilton-Jacobi equations associated with each of these functions, hj. In other words, the Darboux-Haantjes coordinates also are separation coordinates for the Hamilton-Jacobi equations that we are dealing with. And conversely, if we have a set of n independent functions which are separable in a set of Darboux coordinates, then we can find an Haantjes chain and then construct an omega h structure given by essentially this formula. Okay, so but the main message is that if you have a semi-simple omega h structure, then we have privileged coordinates, which allows us to separate the Hamilton-Jacobi equations associated with our problem. Okay, then there are other possible applications, of course. So, generally speaking, any Hamiltonian integrable system from one side admits an omega h manifold associated. From the other side, actually, we can apply this theory to a series of, let's say, relevant or, let's say, standard classical Hamiltonian integrable systems like functional separated system, telescopic system, Gantt-Marker, Steger system, and so on. And we can appreciate that indeed this theory works very well. So in particular, let me just show you this reason why they are in red, two applications, okay? Drag-Holt systems and multi-separable superintegrable systems. Okay, in the case indeed of this Drag-Holt type system, which was introduced by Campo-Morsusberg, Cariniena, and Ragnada quite recently. So we have an integrable structure, okay, so we are in 2 dimensions, and when k1 goes to 0, we have this parameter k1 here, actually, and here. Then the system converts into the quite famous post-Winternitz superintegrable potential. Now, what is nice, well, or what is relevant here is that our system is non-separable, at least in the configuration space. In other words, you don't find coordinates in the configuration space, certainly not orthogonal, but even non-orthogonal, in such a way that you can separate the system. That's why the system was considered simply non-separable. But actually, as we know, is the full space the real, let's say, framework where separability should be considered. And the question indeed is there any coordinate system now in the full space allowing separation of variables? And the answer is yes. And with this Haantjes algebra approach, you can indeed find these coordinates. Indeed, you can first of all construct an omega h structure given by actually two operators, k1 and k2, where k1 is trivial, the identity, but k2 is non-trivial, this one. Then you can apply our machinery and find the Darboux-Haantjes separation coordinates in a quite straightforward way, which are these ones, of course, a bit complicated, but in principle very well defined. So you can just obtain them in an algorithmic way. And also one can appreciate that these coordinates pass the famous Levi-Civita test for separability, satisfied by Jacobi's Piergiulio equation. They are separation coordinates for the non-separable system. But of course, the system was non-separable just in the configuration space. But in the full phase space, you can separate it, for instance, using this new geometry. Okay, and coming back to multi-separability and superintegrability, as we know, superintegrable systems are very interesting for many reasons. In particular, they are often related to the multi-separability, not necessarily, meaning that typically a superintegrable system is also separable in more than one coordinate system, but sometimes this is not true. Sometimes there are superintegrable systems which are non-separable. Okay, anyway, we have this theorem that an integrable Hamiltonian system admits as many inequivalent separation coordinate systems as the number of its independent semisimple abelian structures. Okay, so each semisimple abelian manifold that you can associate to your integral system is responsible for a set of separation coordinates. And indeed, the superintegral system may have more than one structure, and then you can separate, you can find their separation coordinates in a sort of algorithmic way, and then separate them happily, let's say. Okay.
May I? Because I was thinking about that when you have said, indeed. Here you could have even, for example, cosymplectic and more structures. It's really is very nice because it seems that it's pretty much generalizable to many other frameworks.
Sure.
And
Indeed.
you know, things work by Manuel de Leon or Cariñena or many people from this group. What you have been doing in Cabic study. So you have written about cosymplectic, yeah? Maybe?
Yes, indeed.
Contact also, Jacobi. Okay.
Yes,
Even I was thinking about K cosymplectic, K contact, many other stuff. Yes, very nice. Thank you.
Thank you. Indeed, so the new developments we are thinking about are in these directions. First of all, actually, we studied a Hamiltonian system in a magnetic field, which are also very interesting, actually. They have some peculiarities, but with some work also, we have proved that this symplectic anti-geometry is responsible for the separability properties, or let's say the geometric properties. Also, actually, more recently, I'm studying with André Kubo Eisner lifts of integrable models. This is an old procedure which consists in lifting a given integral or subintegral system from the original phase space to a new, bigger one, higher dimensional one, let's say. And so we were studying how the anti-geometry associated also can be extended to the Eisner lifted system, okay, on the top, let's say, on the higher dimensional world. Then exactly along the lines that Javier was mentioning, so we can generalize to Jacobi and of course contact, cosymplectic, etc. Geometries, and this is something that can be done without too much problems. Of course, one should be careful, but yes, indeed, this can be considered. Actually, I'm thinking that I had to, my goodness, I said the 40% of what I wanted to say, so maybe I will escape something, okay? First of all, partial separability, in 2 words. This is an old idea, actually, due to, first of all, this guy, Di Pirro, 1896, and then Steckel, which was in correspondence with Di Pirro, and it consists essentially in finding local coordinates where the Hamilton-Jacobi equation separates into a system of ODEs and PDEs. Of course, this is a generalization of the standard, we can say total separability, in which the system is a system of pure ODEs, right? And in several cases, what is quite interesting is that there are systems like the Calogero modeling with 4 particles admitting only partial separability. Then this notion is more important than one can suspect. It was somehow, let's say, forgotten during lots of time. Only in 1976, sorry, Hava started again to think about this, and Boyer, Kahn, and Miller, Shanura Stelli, Nicky Camera and collaborators. So then, in 2 words, also partial separability can be easily accommodated, well, easily can be accommodated into this entire geometry. Precisely, we have a partial separability, meaning we can produce this partial separation coordinates when we have 2 kinds of Haantjes algebras, either non-semi-simple but of maximal rank, or semi-simple but non-maximal rank. And so in these 2 scenarios, indeed, we can provide Darboux Haantjes coordinates, giving us partial separation coordinates, okay? And this happens in many applications that you don't have total separability, then you have to, of course, deal with what you have. Then maybe you have a PDE with 2 variables you have to solve, but maybe with numerical, numerical algorithms or whatever, you can deal with these PDEs arising from the separation procedure. Okay, and also actually one can think about generalized Steckel systems because you can also consider Steckel matrices where each line does not depend on one coordinates, but depends on one, let's say, a group of coordinates. Okay, Q1 is a set of coordinates, Q2 another set, and so on. And this is indeed called a generalized Steckel matrix. And then you can consider a generalization of the standard Steckel theory for these matrices. Skipping details, unfortunately, let me tell you that these systems that we were considering indeed are, let's say, considerable generalization of the all known systems which are partially separable. The eigen systems, for instance, are realized from the previous one when m is equal to n, and then also the original system introduced by Di Pirro in the 19th century belong to this class. Also the ones by Havas, Cenura, Stelli, Camran, and so on are re-obtainable from this class. Okay, let me skip again this, unfortunately. So we can produce a criterion for partial separability, which is this one. So in other words, a system of coordinates is a set of partial separability coordinates if this condition is satisfied. I have no time to explain its meaning, but it's a sort of generalization of the total separability condition due by Benenti, which is this one, which is also particularly nice, actually, as many things that Benenti did. Okay. Then a little pause, okay? Let's consider a little intermezzo like in music. So who is this guy? Is William of Ockham, the famous Doctor Invincibilis, because as everybody knows, he was a philosopher of the Middle Age, particularly clever, and indeed was able always to gain the competition with his colleagues, philosophers, and he was highly respected. So Occam, among several important contributions to philosophy, also introduced this famous criterion, the Occam's razor, right? Entia non sunt multiplicanda praeter necessitatem, which means that entities must not be multiplied, must not be spread out beyond necessity. So why I'm talking about this? Because actually what I'm doing now is indeed to multiply, to introduce infinitely many new entities, apparently by violating this Occam razor, which is actually something fundamental, because when we introduce a new geometric structure or a new definition, actually we should always think about its real need, right? So not just because we like it or because it could appear beautiful, but it is really necessary, no? So are we violating this principle or not? That's the question. Okay, then indeed, so the necessity, at least in my opinion, to extend entire geometry and to introduce infinitely many new tensors is due to the example that I showed you before, meaning that anti-geometry does not cover all possibilities. There are infinitely many tensors which are not anti-tensor, but which are still integrable. Okay. Then we introduced in 2017 in this preprint the notion of generalized Nijenhuis tensors. Actually, independently, in the same year, Yvette Kozman-Schwarzbach introduced a similar notion, but with a completely different definition, but essentially it's the same idea. Also, actually, we propose a generalization of the Freudian Nijenhuis bracket, and so on and so forth. Going to the point, what is a generalized Nijenhuis torsion of level M? So, is this guy. Precisely, it's a vector value to form where the nth level depends on the level m minus 1. In particular, when m is equal to 1, the zero level is by definition the Lie bracket. And then you get, of course, the standard Nijenhuis definition. But for m is equal to 2, of course, you get anti-torsion, because the anti-torsion is indeed defined, as we said, no? Starting from 4 contributions, each of them involving the standard Nijenhuis torsion. But one can generate more and more torsions from the previous ones. Indeed, we can have the first generalization of anti-torsion, meaning torsion on level 3, where here you have 4 contributions, each of them depending on Haantjes. I don't know if I'm explaining myself. So there is a simple recursive way to generate a tower of infinitely many new operators. Precisely, first of all, infinitely many new torsions, right? And then we can say that A is a generalized Nijenhuis operator of level m if these conditions apply, meaning its m level torsion vanishes. Particularly for m is equal to 1, we have Nijenhuis operator, for m is equal to 2, Haantjes operator, and m equal to 3 and beyond, we have I-level operators. Okay, then we can also have a description in local coordinates of these guys, so this can be done without any problems. And in particular, so this is maybe the most important theoretical contribution of our work. Precisely, where when I say our work, I mean the work I did with several collaborators, in particular with Giorgio Tondo from University of Trieste. So I had the pleasure, and I still have the pleasure to have fantastic collaborators, and I'm very happy about it. So in this paper, actually, we somehow solved the problem that was open at the beginning, meaning what happens if we have an operator which is not a Haantjes operator, right? It is, for instance, just meaning that it doesn't satisfy neither the Nijenhuis torsion equal to 0 nor the Haantjes torsion equal to 0. Okay, then assuming that A is a generic operator with regular eigendistributions, and then we assume that there exists n such that this is true. Okay, so the nth level torsion vanishes. Then we have 2 important results. First of all eigendistributions as well as their direct sums are integrable. And then there exists local charts where A takes a block diagonal form. So, in other words,
Piergiulio,
see, yes.
sorry, maybe I'm a little bit impatient. And the converse, have you tried? It is impossible. Something is missing.
So this is again a sufficient condition. It's not necessary.
Okay. Okay.
Only for
Okay.
m is equal to 2, you have a necessary sufficient, which is Haantjes theorem. In other words, if this applies, then your operator is integrable. But if your operator is integrable, a priori you don't know if there is one of these torsions which vanishes. But the point is that now we have infinitely many more torsions, right? So And then we have infinitely many more tensors that are integrable. So coming back to this example before, indeed, so this operator field has the third level torsion vanishing. And indeed, it is integrable. So in other words, it was neither Haantjes nor Nijenhuis, but is tau-free, as we say. So then this explains why it is an integrable operator. And then also one can block diagonalize it. Of course, here the example is very simple. But the point is that even in 3 dimensions, you already get non-trivial examples of this new, let's say, new kind of tensors. So they are extremely common in a sense. And if you talk about nilpotent operators, for instance, then once again they are higher level operators, as we can prove. So I'm afraid that I have to switch many things. In particular, indeed, what we have is that you have a night cyclic operator, which means that is nilpotent and cyclic at the same time. Then it is necessary, now this is a necessary condition, that its generalized torsion level n-1 vanishes. Okay, so these higher order geometries are quite very recent, I would say. So they have been defined in 2022. So many things should be explored, of course. But let me just tell you that indeed one can consider the Jordan-Chevalier decomposition of an operator field. So this is an open problem somehow, meaning that is it possible to find mathematical or geometric conditions such that there exists a coordinate chart allowing us to write an operator field L as the sum of a diagonal operator and a strictly upper triangle operator. So this problem means, in a sense, that L, which is a generic operator, can be decomposed into the sum of an Haantjes operator and a higher order operator. Because indeed, a strict triangle operator is essentially an operator with a high-level torsion vanishing. And in dimensional 3 and 4, recently, Bolsinov, Konayev, and Matev indeed solved this problem and showed that indeed this can be done. Okay, one can invent higher level Haantjes algebras exactly as before. So now we have algebras where the operators satisfy this higher level torsion vanishing. So then, of course, Nijenhuis algebras and Haantjes algebras are just the first 2 levels. Let me tell you that with the Nijenhuis operators, you can find an algebra only with constant coefficients, not by multiplying by functions. And this gives immediately Haantjes operators. Okay, so one can repeat all these constructions, and also it is interesting that the Bogojelemsky theorem can be generalized, because if you have an higher order operator like this, then also a polynomial in this operator is again an higher order operator, meaning that if A has this m level torsion vanishing, any polynomial on A also has again the same level torsion vanishing. You can block diagonalize these new operators in suitable charts. We have 2 theorems of simultaneous block diagonalization. This one tells you that if at least one operator in a family of commuting operators has a level m torsion vanishing, then all of them can be diagonalized in a block diagonal form. And of course, if you have more properties, you can again block diagonalize, but with finer blocks. Okay, this is essentially the content of this second theorem. Unfortunately, I have to run a bit. Anyway, let me show you here an example of a generalized Haantjes algebra of level 3. So all these operators are neither Nijenhuis nor Haantjes. They are third level operators. So the third torsion vanishes. Okay. Then actually they also commute. This is an example of a generalized Haantjes algebra of third level. And indeed, you can find the coordinates. This is actually quite simple, where all of them acquire a block diagonal form. Okay, I show you just one of these 3 operators. I skip completely this, so one can actually generalize also the celebrated Froelich and Nijenhuis bracket by using indeed this high-level torsions. So one can define an Haantjes bracket of level n with a algorithm procedure. What is the relation between high-level torsions and bracket? This one. Exactly in the way as the Nijenhuis bracket is related to the standard Nijenhuis operators by putting m is equal to 1 here, because actually maybe it's written here. So the Nijenhuis bracket applied to the same operator, but when b is equal to a, gives you the Nijenhuis torsion. Exactly in the same philosophy, under the same philosophy, you can connect the high-level torsions with high-level operators. Okay, and also there is a bunch of properties of this new structure that I have no time to discuss. In particular, the possibility to detect the existence of Haantjes moduli of operators between this by using this binary operation, this that we call the Haantjes binary bracket, and so on and so forth. Another theorem by Poisson. Recently, they used this theory of us of higher order brackets to prove that indeed if A and B are two commuting operators that in a local coordinate chart are strictly upper triangular, then you have that indeed this high-level Haantjes bracket that we defined is equal to 0. Okay, I skip all this. So let me go to the summary. Okay. Then we can essentially say that Haantjes geometry in several contexts offers a natural language to formulate several important problems in classical mechanics. So we have considered very rapidly the notion of Haantjes algebras, this theory of symplectic Haantjes manifolds. In particular, there are two relevant theorems, precisely the Liouville-Haantjes theorem, which generalizes the Liouville-Ardon theorem in a sense, and the Jacobi-Haantjes theorem, which tells you that the Darboux-Haantjes coordinates are separation coordinates for the Hamilton-Jacobi equation. Then we have seen rapidly the existence of a hierarchy of new generalized Nijenhuis tensors. Then the Nijenhuis and Haantjes tensors are just level 1 and level 2. Also, we have generalized Haantjes brackets, but one can even define objects with many entries, not just two entries, which are the multi-value torsion, which I simply escaped. And to finish, let me give a brief summary of the two most relevant theoretical results. The generalized Haantjes theorem, which provides a sufficient condition for the integrability of a generic and non-semi-simple operator when this generalized torsion vanishes. And then indeed, even if the operator is non-Haantjes, you can a priori establish its integrability, where a priori means that you don't need to study the operator, because of course, if you enter into the spectral properties of operator, you discover if it is integral or not. But finding the spectrum is, of course, very difficult. So you want to have an a priori criterion for establishing whether an operator is or not integrable. Then this sufficient, infinitely many new sufficient conditions provided by this generalized Haantjes theorem are indeed the a priori conditions that do not require the study of the spectral properties of the operator. And then again, the possibility inside this geometry, this generalized geometry, to diagonalize simultaneously families of operators. As future perspective, indeed, we want to study generalized hydrodynamic type chains and hydrodynamic type systems, extend the theory to Jacobi, contact, cosymplectic, what we are doing, and once again extend the theorem over forms operators. Of course, many things are known, but many other things, even for the standard Haantjes geometry, should be certainly explored. For the Nijenhuis geometry, there are many recent results, but already for the second level of our tower of tensor, meaning Haantjes tensors, this is largely an open problem. And then, of course, one can think about Stefan Sussman integrability to generalize all this picture, for instance, dropping regularity condition, and so on and so on and so forth. All this somehow work in progress. Then here are some references concerning recent preprints on these extensions of Haantjes geometry, collaboration with Rafa Zuache and Andre Kugu. But okay, there are also some papers that already quoted in this seminar. So now to conclude, thank you very much for your attention. So it was really a pleasure to participate in this Gamma seminar. Thank you.
Thank you very much for your nice talk, Piergiulio. It's been a pleasure. So let us thank the speaker. Okay, so it's been very nice indeed, very interesting. In my case, I have lots of questions, much more than we can answer now. We have afterwards another talk, but let us people to comment. So, is there any other question, remark, comment? Please go ahead.
Sorry.
Asier, I think it was the first because during the talk.
Hey, very nice talk. So, well, I wanted to remark, well, or to rephrase something that you already said, like a justification of why we should study Haantjes besides Nijenhuis is I think it's this Liouville Haantjes theorem, because for example, well, you mentioned already that there are several restrictions on integrable systems to be Hamiltonian in the classical sense. The one that I'm most familiar with is one that you didn't mention by Ruiloya Fernandez. Well, he proves that for an completely integrable system to be Hamiltonian, it has basically the Hamiltonian function to be separable in action coordinates, which is of course very restrictive. And in fact, we attempt, and also you mentioned the generalizations of these results to contact. In my opinion, the quoting medieval philosophy as you, the one true beautiful way to study contact integrable systems is as homogeneous symplectic integrable systems. So
you haven't spent too much time in Poland.
Yes, but this is true. Like this is the way that one obtains results regarding integrability of contact systems. So, well, my suggestion of how to attempt to generalize these results is to study a symplectic and Haantjes structure with also a Liouville vector field or weight vector field, or however you want to call it, that are these three objects compatible with each other.
Yes, indeed.
Indeed, if I may, in that case, it should be quite straightforward. I mean, do it in this manner. But in certain cases, it may happen because it is about dynamics. About geometry, there is an equivalence between two cases. But when you talk about dynamical systems, the systems related to symplectic and contact, they may differ. They have different properties. They may be differences. But in any case, it's a very good manner, I think, to generalize this to contact. For sure, there will be applications. This is my opinion. Okay, so I think that Alessandro, if this is everything, Asier, I think that Alessandro wanted also to make a question. Yeah,
everything.
Please go ahead.
My question is very quick, actually. So, ciao Piergiulio, and so I wanted to ask you. You mentioned that Haantjes is 0 in dimension 2, right? Always.
Always, yes.
I'm wondering if these higher torsions are 0 in some dimensions. Like, so is it true that T3 is always 0 in dimension 3 or T4?
It's a good question, but the answer is no, actually. Indeed, when the first time I thought about this level torsions, I asked myself exactly the same question. And I was thinking that maybe it's a conjecture. One can think that the third level torsion is always 0 on 3 by 3, let's say, tensor. It is false, actually. It is false, actually. So it may happen, it may not happen.
Thank you.
Welcome.
Okay, is there any other question? Quick question, indeed. No. So, Piergiulio, thank you very much for your nice talk. It's been very inspiring indeed. I have been talking to some of my colleagues during the talk, and probably we will talk to you soon about a couple of things, and I will make some questions, or maybe we have some new examples of things that maybe can be interesting to you. We expect. Please send us the slides if you don't mind.
Pardon me?
Could you send us your slides of the talk to
Sure.
publish it on the? It will be nice to have it. Thank you, Piergiulio. Really, we appreciate it.
Thank you. Bye bye.
So